Calorimetry. Calorimetry is the science of measuring heat or energy flow into or out of a system. It's based on observing temperature changes when a body absorbs or gives off energy as heat. Specific heat capacity is the energy required to raise the temperature of 1 gram of a substance 1 degree Celsius. Or it could be 1 Kelvin, since a change in Celsius is equal to a change in Kelvin. And when we look at the units for specific heat capacity, we look at joules per gram degree Celsius or joules per gram Kelvin. Molar heat capacity is the energy required to raise the temperature of 1 mole of a substance 1 degree Celsius or 1 degree Kelvin. So our units for molar heat capacity are joules per mole degree Celsius or joules per mole Kelvin. And we can do conversions between specific heat capacity and molar heat capacity. When we talk about heat, we have a simple equation. And that equation is Q equals mass times our change in temperature times our specific heat for our substance. So we'll look at some problems. Let's say that the specific heat capacity for aluminum is 0.900 joules per gram degree Celsius. It's an extensive property. It doesn't depend on the amount of aluminum we have. And it says that for every gram of aluminum that we want to raise the temperature 1 degree for, we would have to add 0.900 joules. So here's a question. Calculate the energy needed to raise the temperature of 850 gram block of aluminum from 22.8 degrees Celsius to 94.6 degrees Celsius. All right, so the first thing we're going to do is write our equation. Q equals mass times our change in temperature times our specific heat. So we're given the mass of our aluminum sample, 850 grams. We want to figure out our temperature change, so we'll take our final temperature minus our initial temperature. So 94.6 minus 22.8 degrees Celsius. And we'll put in our specific heat for aluminum, which is 0.900 joules per gram degree Celsius. Now, when we look at the units, grams cancel out, degrees Celsius cancel out, and we're left with joules. And those are our units for heat. So we plug our values into the calculator, and we find out that 55,000 joules of energy would need to be added in to an 850 gram sample of aluminum to raise its temperature from 22.8 to 94.6 degrees Celsius. Now, one other thing we're going to do is a unit conversion problem. It says calculate the molar heat capacity for aluminum. Well, here's our specific heat capacity. So we have 0.900 joules per gram degree Celsius. And we want to get it to the molar heat capacity, which is joules per mole degree Celsius. So we're going to do a conversion from grams to moles. It tells us our substance is aluminum. So the periodic table will tell us that 26.98 grams of aluminum for every 1 mole of aluminum. That'll leave us with 24.3 joules per mole degree Celsius. All right, so let's look at a problem that's a little bit more involved. This is an energy transfer problem. It says a 5.037 gram piece of iron is heated to 100 degrees Celsius. It's placed in a coffee cup calorimeter, which is an instrument that just keeps energy in and doesn't allow it to flow into the surroundings, that initially had 27.3 grams of water at 21.2 degrees Celsius. If the final temperature of the water is 22.7 degrees Celsius, what is the specific heat capacity for iron? So here we have an energy transfer problem. We have a hot piece of metal that we're putting into a sample of water. Energy is going to be transferred from the iron into the water. The temperature of the iron is going to go down. The temperature of the water is going to go up until those two temperatures are equal. So we can set the energy lost by the metal equal to the energy gained by the water and solve for our specific heat capacity for iron. So we're going to have two sides to our equation. We've got the metal and we've got the water. The metal is going to lose energy. The water is going to gain energy. And theoretically, the energy lost by the metal will equal the energy gained by the water. So mass times the change in temperature times the specific heat for the metal will equal the mass times the change in temperature times the specific heat for the water. Now, since we're losing energy here, we're going to put a negative sign. So we'll plug in our variables. We've got 5.037 grams of our metal. Our temperature is going to go from, we're doing final to initial, 22.7 minus 100. Because the final temperature of the metal will equal the final temperature of the water. And we're trying to find the specific heat for our metal. And then we'll plug in all the information about our water. So the mass of the water is 27.3 grams. We'll do final minus initial, so 22.7 minus 21.2. And then we'll multiply that by the specific heat for water, which is 4.184 joules per gram degree Celsius. And that's a number that we just need to know. You're going to use it often enough that you'll just remember it. So we find our temperature changes. Negative 77.3 degrees Celsius as our metal loses energy, and positive 1.5 degrees Celsius as our water gains the energy. Now we're going to solve our problem. We're going to multiply 27.3 times 1.5 times 4.184. We'll divide it by 5.037, and we'll divide it by positive 77.3. And that's going to give us 0.440 joules per gram degree Celsius. And that's our specific heat capacity for iron. Now we're going to look at a problem that deals with making solutions. We're going to take solid sodium hydroxide, dissolve it in water, and since it's an electrolyte, it's going to break up into sodium ions and hydroxide ions. And we're told that during this particular process, our delta H for our reaction is negative 43 kilojoules per mole. Now, the negative sign means that the sodium hydroxide is going to lose energy as it dissolves. That makes it an exothermic process. We could actually take this number and plug it into our equation by adding it on this side of the equation. So for every mole of sodium hydroxide that dissolves, 43 kilojoules of energy are going to be released. So let's say we take 14 grams of sodium hydroxide and we add it to water, and we want to find out how much total energy is going to be released. Well, it's a stoichiometry problem. For every 1 mole of sodium hydroxide, 43 kilojoules of energy. So if we take our 14 grams of sodium hydroxide and convert it to moles, 1 mole of sodium hydroxide is 40.00 grams of sodium hydroxide, then our balanced equation tells us for every mole of sodium hydroxide that dissolves, 43 kilojoules of energy are going to be released. Now we have much less than 1 mole of sodium hydroxide that we're dissolving, so we're going to have much less than 43 kilojoules of energy being released. So 14 divided by 40 times 43 gives us 15 kilojoules. So if we have a sample of water and we add 14 grams of sodium hydroxide to that water, 15 kilojoules of energy are going to be released from the sodium hydroxide, which is considered to be the system, into the water, which is considered to be the surroundings.